All right, we'll take another look at voltage and current division. In the last video, we looked at voltage division. In this video, we'll look at current division. We applied voltage division to two resistors in series. We'll apply current division to two resistors in parallel. And again, this will apply to any number of resistors in parallel. We'll just show it for two resistors in parallel. Voltage division, we used KVL and Ohm's law. Current division, we'll use KCL and Ohm's law, so that we can shorten our process, and instead of having to apply KCL and Ohm's law, we'll just be able to apply current division. So our KCL equation is up here. This is KCL. And here for I1, Ohm's law, I is equal to V over R. And so our voltage V here is across both of these resistors. So I1 is V over R1, I2 is V over R2. So there's our Ohm's law. And here now, of course, we can pull out our common variable V, and we get that 1 over R1 plus 1 over R2. And this looks like similar to the process we used when we were solving for with voltage division. So that's written out there. Pull our common variable V, and then we can solve for V. So V then is equal to I divided by the sum of these 1 over R1 plus 1 over R2. So whereas R is the resistance, we could also write that as this is equal to R I times, or I divided by, 1 over R1 is G1 plus G2, where of course G1 is equal to 1 over R1, and that's our conductance. And G2 is 1 over R2, and that's our also conductance R2. So if we continue with that, what we want to find then is I1 and I2. We can say then that I1, that's V over R1, or it's V times G1, and there's our G1, which is 1 over R1, and we'll divide that by, take our voltage is I divided by R1, G1 plus G2, or 1 over R1 plus 1 over R2. So here's our divider. So this then, we'll write it this way, but it's important to recognize that what this is it's really equal to this G1 divided by G1 plus G2 times I. So where with voltage division, we took the resistor that we wanted the voltage across and we divided by the sum of the other resistors. Current division, we take the conductance of that resistor and divide by the sum of the conductances of the other resistors, of all the resistors. And that gives us the current through just the one resistor there. So in general, we can write that for n resistors, it's the current that is flowing into all of the resistors. And the way we divide that is with the conductances or the reciprocal of the resistances. So I'll write this again as, we could write that as equal to our I times GK over G1 plus G2, that conductance Gn. So that's our current division in the general case for n resistors. And again, if it's just two resistors, we could also solve this saying, okay, I2 is equal to V over R2. Well, that's true. That's our Ohm's law. And what is that voltage V? That voltage V is this current flowing in times the equivalent resistance of these resistors in series, in parallel. And these two resistors, we can use the product divided by the sum R1 in parallel with R2. That's the product divided by the sum, and then we can see, well, these R2's cancel, and we have I2 is equal to I1 times R1 divided by R1 plus R2. Remember, if we had two resistors in series, R1, R2, and we have this voltage V across the series combination of R1 and R2, then we could say, well, we'll go to we'll look at V2. V2 is equal to V times R2 over R1 plus R2. So we take the opposite resistor. So this is, again, we could also say this is equal to I times G2 over G1 plus G2. So there are different ways of looking at that. So, but we check to make sure what we have is the for the larger resistor, we're going to have the smaller current flowing through the larger resistor, so that we have the same voltage across. And in series combination, then for the larger resistor, we have the larger voltage across the larger resistor when we have the same current flowing through. So again, in general, we still get the same case for our current division. Again, if we were going to compare the current division to the voltage division, and frequently we'll just have two resistors, so it's nice and quick to say, well, okay, with two resistors, the larger when we're doing our voltage division, we take the resistance of the resistor that we're trying to find the voltage across, and we divide that by the sum of all the resistors, multiply it by the voltage across the series combination. For current division, we take the other resistor, right? So, and we divide that by the sum of all the resistances and multiply that by the current that's being divided between the two. So let's do a quick example here. In this circuit here, we have quite the resistor network being driven by a current source, and we have the different currents labeled. We have IS through this branch. We have I2 through this series combination of these two branches in series. We have I1 flowing through from the top node to the bottom node through this resistor network, and IX just flowing through this 30 ohm resistor branch. But we want to determine is IX given that we know I1. So we really only need to look at this part of the circuit over here. Even though we have more stuff going on over here to find I1, this I1 is going to flow in, and it's going to have to be divided between the 15 ohm and 30 ohm resistor. So we can use current division here. We could go through and we could try to find the parallel combination. We could find voltage division. There's a number of ways to do this, a little bit more complicated. But if we could just do a current division on this if we recognize it, and we can see that IX is going to be equal to I1 times 1 over 30 ohms, right? Because that's the current IX is flowing through, divided by 1 over 15 ohms plus 1 over 30 ohms. And we lost the pen again. 1 over 30 ohms, or it's equal to I1 times, if we multiply through by the 30 ohms times 15 ohms. So if we multiply by 30 ohms times 15 ohms, we end up with our 15 ohms divided by 30 ohms plus 15 ohms. So we have the other resistor in the numerator, and that gives us what, 1/3. So it's equal to I1 times 1/3. We can substitute then in for I1, 100 milliamps times 1/3, or is equal to 33.33 milliamps. So that of course means that if this IY, so we can do our check. IY must equal by KCL, IY flowing out must equal to I1 flowing in minus IX flowing out, or that must equal 66.67 milliamps. And then what should be true then is that VXY is equal to IY times 15, and it must also be equal to IX times 30. And of course, that checks. All right, we'll look at some more examples in later videos.